Okay, hey, I wanted to make a video to kind of go over some of the highlights of these free response questions from chapters 5 and 6. I feel like these two chapters are two of the most difficult chapters that we had looked at last semester based on probability, binomial distributions, things like that. So this first one was looking at these two different antibiotics used as treatment. It mentions that for antibiotic A, it can effectively cure an infection 60% of the time, okay, on its own, and the cost for antibiotic A is $50. Okay, and then antibiotic B, it can cure the infection 90% of the time, but its cost is $80. Okay, and I started my workout for part A down here, and then I didn't ran out of space, so I had to go up above here. Okay, it says that the antibiotics, they work independently. They can both be administered to children. And so here are the two different treatment plans. Okay, plan 1, they start out with antibiotic A first, and then if that is not effective, then they move on to antibiotic B, whereas in plan 2, they begin with antibiotic B, and if that's not effective, then they move on to antibiotic A. Anytime a problem feels like there's different phases, like you do this first and then this, that is a really good problem to try these tree diagrams that we learned back in chapter 5, okay? So here, I started out labeling this as plan A, and I kind of marked off, okay, if plan A works and the person gets cured, I'm sorry, that's plan 1. If the person gets cured taking antibiotic A, they told us up here that happens 60% of the time, then great. The odds of them being cured on that path is 0.6. Okay, the other option is 40% of the time they're not cured. So if they're not cured, according to plan A, if that's not effective, then we're going to go ahead and apply antibiotic B, and which they told us up here, antibiotic B is effective 90% of the time. Okay, so if I'm following this path, remember you multiply across these branches, the probability that A did not work and B worked is these two things multiplied together. Okay, so if I want to figure out the total, what's the probability that a child could be cured using plan A? There's two paths. It could either be this or it could be this. So I'm going to take these two values, I'm going to add them together. There's a 96% chance that they could be cured with plan A. Okay. Then up here you can see I basically worked the same logic with plan B, making the tree diagram very similar, multiplied through the branches there. Oh, I guess it was this way. Multiplied through the branches there and then added these two options together. And you'll notice that we get the exact same probability, which is what that's going to kind of play a role here with some of these other parts, okay? Part B says, compute the expected cost per child when plan A is used for treatment, and then same thing for plan 1 is used for treatment, and then same thing for plan 2. Okay, so the expected cost, now remember, up above here, it mentioned that the cost for plan A was $50, the cost for plan B was $80. So you can see here, for plan A, okay, if that works, okay, if plan A works right out of the gate, okay, 60% of the time, you're only going to have to fork out $50, okay? But if you're not cured that 60% of the time, and you're down here at this 40% where you're not cured by antibiotic A, now you're forking out this other $80, okay? So we're talking about 40% of the time you've spent the initial 50 and then an extra 80 on top of that. Okay, that's why this is a 130, because 40% of the time you spent the initial 50 and then also had to spend the 80. Okay, these multiplied together give you plan 1's expected cost of $82. You can see I essentially did the same thing here for the expected cost for plan B. Okay, so the costs are almost the same. The probabilities are the same that someone would get cured. So for part C, it says, based on your results in A and B, what would you recommend, and explain your recommendation? And I just said, since both the plans result in the same probability of being cured, plan 1 is slightly better because it has a lower expected cost, $82 instead of the $85. Okay. Okay, for this next one, this is talking about an automobile company. They want to learn about customer satisfaction among the owners of 5 specific car models. They have very large sales volumes that they have recorded here for these 3 models, A, B, and C, but these other 2 models, D and E, are recently introduced, so they have smaller sales volumes. You can see what's been recorded in the last 6 months is a total of 297,354 cars that have been sold. Now these numbers you see that I wrote underneath here that help me with a later part of the problem. What these are is these are basically me taking the amount of cars for Model A, and I was dividing that by the total amount here, and I was getting that Model A represented 38% of that sample of 297,354. Okay. Now, it's asking here, it says the company can obtain a list of all the individuals who purchased new cars in the last 6 months for each of these 5 models. The company wants us to sample 2,000 of these owners, okay? So they're wanting to sample like 2,000 of all of these. Okay, it mentions here, for a simple random sample of 2,000 new car owners, what is the expected number of owners for Model E, and what is the standard deviation for Model E? Okay, this would be where we would use these formulas here on the formula sheet. Okay, for the P, which is like a probability of a success, that would be the likelihood of someone buying Model E car here in the last 6 months. That's where I got the 0.008 from, and you can see how I just plug those into the formula. Okay, for part B, it says, when selecting a simple random sample of 2,000 new car owners, how likely is it that fewer than 12 owners for Model E would be included in this sample? Okay, so the question is, what's the likelihood that we're talking about less than 12? Now, here's where you're going to have to be a little bit careful. This is a binomial problem, okay, because we know the probability that someone would buy a Model E car is this 0.008, so that's our P. Okay, we know of the 2,000, that's like our fixed number of trials. But the trick is, when you use binomial CDF, this is exclusively a less than problem, okay, but it's actually a less than or equal to. So whatever number you are putting in right here in this spot, it's going to include that number, which I put an 11 there, and everything less than it. You'll notice the way this is worded, it says fewer than 12. So I don't want to count the 12. That's why I put an 11 in. Had I put a 12 here, then it would have calculated everything 12 and under. Okay, you'll see I have a different way of doing this on here as well. I have like this, or I don't know that I would mess with doing it that way, but you can see on the rubric that I attached, it gave an alternate way of doing that, which you're welcome to do it that way as well. Okay, and then down here at the bottom, it's asking if the company is concerned that a simple random sample of 2,000 car owners would possibly only include 12 owners of, or fewer than 12 owners rather, of Model D and fewer than 12 owners of Model E. That's what their concern is. They're asking you to briefly describe some type of sampling method where you would pick 2,000 owners, and it would ensure that you would get at least 12 owners from each of the 5 car models. Okay, and so I am describing taking a stratified random sample where each car model is a strata or a group. Okay, and we're going to take a proportion from each car model that's equivalent to the percent of the 297,354 cars sold in the last 6 months. And those were these numbers that I had put up here earlier. I had listed like what percent those cars make up. So if we're looking for a sample size of 2,000, and then we could say, well, we want 0.008 of that 2,000 to be how many cars we would sample for Model E. Okay, so for example, I think I started on the left. Model A, 38% of 2,000 would mean 760 cars, so we should sample 760 cars. Okay, for Model B, I think it was 32% were Model B owners. So 32% of 2,000, we should survey 640 cars. And I worked that out with all of them. You can see even in Model D, if we do the percentage times 2,000, there'd be 22 of those cars, and Model E, there'd be 16. Okay, obviously, I made a little note here off to the side that the car owners would be selected at random within each of those groups there. Okay. Okay, this one was talking about the egg cartons. It mentions up above here that a full carton of eggs that has an empty cardboard container and 12 eggs in it is normally distributed with an average weight of 840 grams and a standard deviation of 7.9 grams. Okay, and that's all summarized right here. Part A was easy. That was just a normal CDF. I'm not going to talk through that, but that was pretty easy. Part B was asking you to kind of break down what the average weight was for just a single egg. Okay, so they tell you up here in the problem that if you have an empty cardboard container, the average weight of an empty container is 20 grams. Okay, the standard deviation is 1.7 grams. Okay, 1.7 grams. We're going to assume all these are independent here. This is asking us to figure out what would be the weight of a single egg. Okay, so keep in mind up above here, the 840 is a full carton of eggs. It's got the cardboard carton and the 12 eggs in it. And so on this side, we would take 12 times, we don't know what the average weight of each egg is, so we're going to leave that as mu sub x, plus the average weight of an empty cardboard container. You're just using algebra, working backwards. This gives you approximately the average weight of a single egg. You have to be a little bit more careful when you're calculating the variance. It wants to know what's the standard deviation of an individual egg, okay? Because when you're combining standard deviations, you really have to combine variances. Again, the left side represents the full carton. So if you scroll back up to the top, you can see the standard deviation of a full carton of 12 eggs is 7.9, but notice that I squared that, so this is representing the variance. Okay, that would be equal to 12 times the variance of an individual egg plus the variance of an empty carton, which we're told up here in Part B, an empty carton standard deviation is 1.7. That's why I squared it. Then all I did here was just used algebra to solve backwards. Keep in mind the variance is the standard deviation squared, so that's why at the end I took the square root. Okay, the last one here is, again, another probability problem. This is talking about having 9 sales representatives, 6 men, 3 women. They all want to attend this national convention. There's not enough funds. They can only send 3 people. So the manager picks 3, and the 3 people he picked were women. And people were concerned that there were no men selected. And so we want to calculate what's the probability that of the 9 people with this amount, 6 men, 3 women, what would be the odds that you reached in and you just randomly selected out 3 people and all 3 people were women? Okay, this is not a binomial distribution for several reasons. One is the fact that the probability of a success is not fixed. As soon as you select someone, that's supposed to say fixed, as soon as you select someone, you're not replacing them back in. So this is not a fixed probability. Okay, all you're going to do is just say, okay, well, the odds of the first person that's chosen being a woman would be 3 out of the 9. Okay, and then now with 1 person removed, now there's only 8 left, and now there's only 2 women left. And then the odds of the third person being a woman, well, that's the 1 remaining woman, and there's only 7 left. You multiply that together. You see the odds of this happening is very unlikely. It's 1.2%, and that's what we're looking at down here. It says, based on your answer, is there reason to doubt the manager's claim that the 3 people were selected at random? You can read what I have here. It's underneath that 5% threshold, so it seems very unlikely that that could have happened. And then on the back, and you can just pause this to kind of read my description, but it's talking about using dice to kind of simulate this, and would that be okay? Dice would not be okay to simulate this. I think that you could read this description and kind of get the gist here from my answer. I don't need to explain anything. I'm trying to keep these videos under 15 minutes. If you have further questions, please contact me.